Welcome. We are now ready to take a look at finding the mean, standard deviation of a variable that follows a binomial distribution. So let's jump in with the example. So suppose a bakery has historical data and knows that 80% of customers who purchase cookies at their bakery select chocolate chip as their flavor of cookie. We randomly sample 8 customers who made a cookie purchase at the bakery today, and we'll let X represent the number who selected chocolate chip as their flavor. All right, so first, let's just make sure we talk about that we do have a binomial experiment going on here. So N, the number of trials, we're talking to 8 customers, so that would be 8. And then P is the probability of a success on a trial. And based on the bakery's historic data, the probability a customer buys chocolate chip as their flavor cookie is 80%, so 0.8 in decimal. And Q then would be the probability of a failure. So the complement of P, so Q is 1 minus P, so 1 minus 0.8 would be 0.2. So if there's an 80% chance the customer chooses chocolate chip as their cookie, then there is a 20% chance they choose some other flavor cookie. All right, and the probability distribution is graphed here. So X is the number of customers in our sample who chose chocolate chip. So just some possibilities here. Out of 8 customers, maybe 6 chose chocolate chip cookies, or maybe just 2 did, or maybe all 8 did. So there are different possibilities for the number of customers in the sample who chose chocolate chip. Now, what I can see here on the graph is that more of the probability is here at the higher end. So more of the area is up here. And that's because the probability of picking chocolate chip is more than 50%. So we end up with this graph that has this skewed left shape. All right, so let's move forward then and find the mean. So it says estimate the number of customers in the sample who selected chocolate chip by giving the mean of the relevant distribution. This is also called the expectation of the random variable. All right, so the mean or expected value, the formula is going to be very simple when we're working with a binomial random variable. So we'll write that here. So the mean, population mean, mu, for this random variable is just n times p. So N was 8 customers times the probability a customer buys chocolate chip as their cookie choice. And then if we multiply that, 8 times 0.8, we average 6.4 customers. So on average, for every 8 customers, I expect 6.4 to purchase chocolate chip. Okay, so you can't literally have 6.4 customers on any individual group of 8, but here's again what this idea is of long run. So the mean is called the long run population average. So what it means if we talk to a sample of 8 customers and wrote down how many of them bought chocolate chip, like 5 of them, and then we talked to another 8 customers and maybe 7 of them bought chocolate chip as their cookie, and then talk to another 8 customers and maybe just 1 of them chose chocolate chip as their flavor cookie. If we keep talking to 8 customers over and over and over again, and we recorded the number of those who did buy chocolate chips in the sample, and then average those numbers, that's what comes out to be the 6.4. All right, so up on my graph here, just going to sort of approximate and draw a little arrow here, triangle. So the mean is 6.4, but there's definitely going to be variation in any individual group of 8 people that we sample. So along with measuring the mean, in this section, we'll take a look at the variance and standard deviation, which are measuring deviation differs away from that mean value. So there are other possibilities here as we're looking at 8 customers, and that's what we tried to talk about as we're looking at variance and standard deviation. So it says quantify the uncertainty of the estimate by finding the variance and standard deviation of the distribution. All right, so we'll start with variance, and I know we haven't used this much, but variance is sigma squared. So the random variable x. So that's our symbol for population variance. And the formula is still going to be pretty simple. Now it's just NPQ. So we take N times P, and then our Q was 0.2. All right, so 8 times 0.8 times 0.2 is 1.28. And we won't work with variance really until closer to the end of the semester. What we'll be working with more is the standard deviation. So for population, the symbol is sigma. So this is our population standard deviation. And standard deviation is always the square root of the variance. So up top, you'll see I wrote the formula is the square root of NPQ because the variance was NPQ. So once you have your variance, you can just take the square root of your variance value, and that gives you your standard deviation. So we'll do square root of 1.28, and the directions say round to 3 places as needed. So we'll do 3 here, 1.131. And oops, sorry, 1.131, 131. And now these units would be customers. So it's measuring again deviation away from the mean. And it's really always harder to sort of conceptualize concretely standard deviation. So we just want to keep in mind that it just means that there are going to be differences every time we talk to 8 people away from the estimate here, a mean of 6.4 customers. All right, let's do one more. And on this one, it says Chester historically has an equally likely chance of catching a Frisbee as not catching it. And I'm going to give him 8 attempts to catch a Frisbee. X will be the number he catches. All right, so we'll be estimating the mean. So we have a binomial distribution again with N8. And now the probability he catches it, since it says it's equally likely he catches it as not, that means it's basically a 50-50 split, 50% chance, 0.5 he catches it, 50% chance, 0.5 would be the chances he doesn't catch it. So success probability, failure probability. And now because those are equally likely, we're going to see a symmetric graph that's starting to look bell-shaped here. So the mean, mu, on average, how many would I expect him to catch? So n times p. So if he has 8 tries, then on average, I would expect him to catch 4 of them. So 8 times 0.5 is 4. All right, and I can see on my graph that 4 there is right in the center of the distribution again because of equally likely chances of success and failure. So if I give him 8 tries, some days he'll catch 4. That's actually most likely the highest probability bar there as an individual result. But it's possible he only catches 1 Frisbee out of 8. He could have had a bad day, or maybe he catches all 8. So there's going to be variation, but the averaging will be 4. So if he's given 8 attempts and we repeat that process over and over again, on average, I do expect him to catch 4. But then let's measure deviation away from that by first starting with our variance. So sigma squared is NP. So 8 times 0.5 in this case is just 4. Half of 8 is, I forgot the Q. Oh my gosh, that was just the mean again. Sorry, the variance, NPQ, there we go. So N was 8. P was 0.5 and Q is also 0.5. There we go. All right, so 8 times 0.5 times 0.5 is going to be 2. And then standard deviation is just the sigma. So sigma is just the square root of the variance. So you'll just do the square root of the variance that you just got. So square root of 2, square root of 2, and that's 1.414. So a standard deviation of 1.414 catches. All right, so those formulas apply to a variable that follows a binomial distribution.